So, hi. So the project is about energy forecasting in commercial building using property features and natural sources. The study focused on developing machine learning models to forecast energy consumption in commercial buildings using CBUG's 2018 dataset. So the motivation for this project is like growing importance of sustainable energy management in commercial buildings. The key reasons include the rising energy costs and consumptions. The commercial building account for a significant share of global energy use. Like from 2018 to 2012 to 2018, energy consumption cost in commercial buildings rose by 14%, and like amounting to approximately $141 billion. So that much of increase is there. And coming to the environmental concerns, the carbon emissions resulting from fossil fuel usage are a major contributor to climate change, because uh, traditionally, in earlier days, coal is used for the energy, for making the electricity. So that will lead to the environmental, that will emissions like carbon emissions is there. So that will lead to the uh, major concern about the climate change because of, uh, and the and there is a strategies to enhance energy efficiency and incorporate renewable energy sources like wind, solar, etc. For the electricity. So that will reduce the reduce the usage of other materials. So next one is about the operational challenges. The complexity of managing energy use in building arises from factors like occupancy patterns, like some buildings are vacant, some buildings are not vacant. So it also related to the occupancy of the buildings, and also the climatic conditions. Some buildings are having not so sorry some areas are having colder regions, so there will not be any other source for electricity. So most of the people use heating for, because it's too much cold, so they will use heating. So the cost is also high there for heating, and some areas are hotter regions, so there will not be any heating needed. So that area, the consumption will be low. And also the uh, climatic condition. About the building characteristics. Some buildings is build like some buildings are older, some buildings are new. So older buildings tend to take more consumption because they are not that much isolated. So for the newer buildings, the that are more isolated, so it will not take more electricity for. And also the post-COVID-19, the fluctuating occupancy level have further complicated energy usage patterns. Like after the COVID, the most of the people are inside the house, like work remotely. So that will also increase the energy consumption, and also the technological advances, the increasing deployment of smarter technologies in buildings. There is a pressing need for data-driven and predictive solutions for the energy consumption. So this research seek to develop models for predicting energy consumption using property features and natural resources, enabling building managers to make informed decision about the energy efficiency, how they need to build the new buildings for the future to reduce the consumption. So coming to the literature review, the key literatures are Deng, Ital, and Bourdieu in 2019 and 2018. The Deng used a 2012 dataset to predict energy use intensity in commercial buildings, because in 2018 only the 2012 dataset is only there for the prediction. So and now in 2023 November, only the 2018 dataset have been published. So this will be a first dataset for the prediction for the energy consumption. And they applied machine learning techniques like support vector machines and random forest. Their findings are machine learning methods improved accuracy by 10 to 15% compared to the regression models. And they also highlighted gap in predictive power due to missing variables like document behavior and thermal performance. Coming to the board in 2019, I reviewed methods integrating document behavior into energy prediction models, discussed statistical regression, decision tree, and artificial neural networks. And also their findings is including human factors significantly enhance accuracy of the predictions. And the humans interaction then will relate to the accuracy of the predictions, and also suggested combining traditional statistical methods with the machine learning for better results. And then coming to the methodology part, here for this research, I used a 2018 commercial building energy consumption survey. It's a survey CBEX data sets. It can be get from the website EIA, and it is a public data set. It is consists of 6,436 observation and 1,249 variables. Coming to the pre-processing, we have some missing values, like some variables is having more than 4,000 missing values. So we remove that variables. It's about like 20% of missing data, we remove that variables. And also we apply log transformation to the target variable, like the target variable is highly right skewed. So we apply the mainly the data set, the target variables scale is about the lowest kilowatt is like 36 and the highest one is about 11 million. So that will be a huge change like will be there. We used a log transformation to uh, get a proper scale. So to get a normal distribution, then we used principal compound analysis to reduce the dimensionality, retaining 95% of variance with the 257 components. Like about 1,249 variables are there. So after the PCA, we got like 257 components. And then after that, we developed the models. Like we implemented for models like random forest, XGBoost, and linear regression and ridge regression. Coming to the results, XGBoost is having the low mean squared error and having low mean absolute percentage error, and it shows the best performance comparing to the other models. And all the models achieved about less than a 6% of mean absolute percentage error. So coming to the random forest model. I also provide a robust performance and effectively captured feature interactions and variability in energy consumption. Coming to linear regression, provide a baseline metrics for the comparison, and also ridge regression addressed multi-collinearity issues and stabilized predictions. However, its performance was only marginally better than linear regression. So the energy source findings are like the natural gas was most commonly used in the buildings other than the electricity. Then only the solar is only used by only 2% of buildings. So this study, uh, the main research contributions are like it is the first study using the CBEX 2018 datasets, and it's also identification for energy use patterns, and this will make a framework for future research. And and that's it. Thank you. This is the code artifact. So coming to the code, first of all, uh, I just make two notebook, like it's a same one, like uh, one is just already run. I already run the code because it will take too much time for running the code. So that's why I make two code, just a copy of that code. For the first code, it is already got the output, so I can see from here. Here, just I will run the code. So for the time consuming part, I will switch to the already run the code. So starting from, I just import the libraries and everything. And then I just start run, checking the shape of the data set. The data set is like 6,436 and 1,249 variables. Coming to the summary, there are 1,249 variables and one dependent variable. It's ELCNS. And just take the head of the dataset. Then about the data types, like identifying category and numerical columns. We only have the numerical columns only because it's a regression dataset. And coming to the I just check the unique values that are having in the PBI is a variable which shows the these numbers are the just buildings names, like two is corresponding to office, it is corresponding to some other like hospitals, etc. So and I just check the target variable LCNS, and it's having unique values like its minimum value is like 36, and the maximum value is about 11 million. Uh, and then I just take the check the info, the data types, then check the summary statistics. Here we can see the count, mean, standard deviation, and the minimum value and maximum value of different variables. And just check about the maximum value of the target variable, and just remove the minimum value. And the summary status or continuous. I just check the summary status or continuous variable. Then I check for the pre-processing stage. I check for the checking missing values. Just check the missing values. Some of the variables are having so much of missing values. So I just remove the variables having more than 4,000 of missing values. Mm, then I just check the some of the variables we applied a mean imputation to for the missing values, like just a mean value for the previous value to solve the mean. So then again check the missing values, and then after the removing some relevant variables like more than 20% of missing data, and we check the shape of the variable data set. We got 963 variables. After that, we done some visualization, like uh, these are the count of the variables, and this is the uh, different types of variables, no, different types of buildings, and also check the total energy consumption. Like the fire station and police station, the building having more consumption. Then check the natural energy source distribution, like natural about 70% of buildings using natural gas, only 26% using fuel oil. And check the electricity consumption summary, like natural gas and the difference between natural gas and the electricity. So this is just a bar plot showing like this much of most of the buildings are using electricity only. A little bit of buildings are using only natural gas. Then because I done specifically for natural source variables and EDA part. So these are the variables which are related to the natural resource variables. So these are the natural gas and other fuel used and other variables. So I just take the summary statistics of that variables also. Then I just calculate the mean and everything. I just normalize using the min max scaler. Then again taking to some of the statistics, just visualized visualized the natural sources across the different building types. Like, these are some visualizations. And I just check the correlation of square feet with the natural energy sources. Just check the p-values using Pearson correlation coefficient. I think this will again take time, so I'm just switching to this data set. Sorry, this code. So here we stop. So we just just check the correlations and the p-values. We check the variables having most highest correlation with the target variable for the natural source variables. Then just plotted a heat correlation map. Then just check if there is any value variables is having non-values. Then we check the p-values of the all variables in the data set. Then we log transform the target variable, because the target variable is right skewed, and we can see from here. When I check the plot, we can see it's right skewed. So we log transform it, and also we added +1 to avoid the zeros. And after log transformation, we're getting a normal Loma scale, and we check the box plot to show the outliers in the target variable. And we check the target variable. Then we check the range of the target variable. In the original scale, the target minimum value is 36, and I already tell, and the maximum value is 11 million something. So we converted to into minimum value is 3 point and to maximum value is 18. So the range is about 14. So to get a normal distribution, we check the range also. Then we calculate the number of outliers. So percentage outlay is 9.57. So after when we check the log transform target variable, there is only little bit of outliers. So that's why I used log transform target variable, and we just check the correlation with the dependent variable plot. And ELB2. ELB2 is also it's a electricity consumption variable. It's same as ELCN. So ELB2 is both are perfectly correlated. It's just a duplicate variable. ELB2 is the electricity in British thermal unit, and ELCN is in kilowatt. So that's the only difference. And we treated the missing values. Then we checking for the outliers. And from summary slides, we can see all variables are highly skewed. So missing values feature correlation greater than, we just check the missing values greater than target variable. So we already treated, so there is no missing values. So on the summary statistics or highly correlated, we just check the summary statistics, so highly correlated variables. There we can see the then we get treated the outliers. So here we can see there is more skewness. So after the treating the outlier using the IQ method, so you get a stable. The original skew is like is like that. So it is reduced and it's transformed. So so we remove some duplicated variables after treating the outliers. So it's the same as the state. So now there is a duplicate variable of 97. So we remove that. Then we apply the PCA, principal common analysis. So we got about number of components needed for 95% which is 257. So check the PCA components also, and then check the variables, 257 variables which are more the PCA command variables. Then we again reverse log transformation for modeling, and then we just uh, starting to the model development. We just developed the random forest model. So we got MSC of 9112 and mean absolute of 5.6794. And we also check the adjusted R square. So adjusted R square is the main before the R square is 78 and the adjusted R square is 75.7538. So there is only a slight difference. So there is only slight difference. So its accuracy is also meaningful. So we just also check the using the original scale data set. So we are getting we need to know how the what is the values we are getting in the original scale to get a proper idea. Then we done for HCV boost. So we are getting a mean score of 82 and R square of 81. We also done hypermanometer tuning using random search. We got an R square of 83. And we done linear regression model and we got a mean square of 9280. And we also done the ridge regression. We got both are almost same valuation results we got. Then we also done the hyperparameter for random forest also. And model evaluation, the best model from randomized research got the MSC of 8954 and the R square of 7918. Okay, that's it. Thank you.